So we're going to talk about, so this is based on a joint work with Michal, Feldman, and Zhihao, Gavin, Tang. And we're going to revisit the profit inequality problem. So in profit inequality, we have n rewards that arrive online, and they come from known distributions, and they come in an unknown order. And the goal of the decision maker is to pick one of the rewards. He needs to do it in an immediate and irrevocable way, which means that whenever it is presented with a reward, it needs to decide whether to accept it or reject it. And the goal of the algorithm is to maximize the expected chosen reward. And traditionally, we measure our algorithms by the benchmark of the competitive ratio, which is the expected value of the optimum over the expected chosen value of the algorithm. So what do we mean by the expected value of the optimum? So usually we want to upper bound what we can achieve. So one, we cannot achieve more than the maximum value that appeared, the maximum reward. So the competitive ratio usually measures the expected maximum of the stream over the expected value of the chosen by the algorithm. And so it is also known as the profit inequality, because you can think of it as an algorithm that can foresee into the future and choose always the maximum. So this is the main concept. And we know that with respect to this problem, we can achieve a tight competitive ratio of 2 approximation. And moreover, even if we know the order of arrival of the rewards in advance, like we cannot improve upon it, like we can get the 2 approximation. And this 2 approximation even can be achieved by a simple single threshold algorithm. Just calculate a threshold in advance based on the distributions and pick the first element, the first reward that exceeds this value. We can get the tight result. So we said that even if we know the order, if we don't know the order, we can get 2 approximation. This is the best we can do. So lately, there is a new line of works that instead of comparing to this benchmark of the best, the optimum offline of the profit, started to consider compare to the new benchmark of the best online algorithm. Okay, so you might ask, so if we design an online algorithm and we compete against the best online algorithm, why not just not use the best online algorithm always gets the best? So this depends on what do you know about the arrival order. So if you know the arrival order, indeed, you can get the optimal algorithm just by calculating the best thresholds. This is a very simple algorithm that can do it by a backward induction, and you can get the optimum online. But if you don't know the arrival order, then things become more complicated, and this is the focus of today's talk. We're going to consider what an algorithm that doesn't know the arrival order of the rewards can do compared to the best online algorithm that might know even the arrival order, or like you can think of it as this. And the next thing you can ask is, why should we care about this new benchmark? We already have an old benchmark that works well, like we have a tight result of 2. We know that we cannot do anything better. And moreover, we can also, the tight result tells us we can just use a simple single threshold algorithms that can be implemented for many settings. And so the reason that we might want to consider new benchmarks are that, first of all, we want to compare to a more realistic benchmark. Like we want the benchmark to be as close to what we can achieve. In general, you don't want to compete against something that is very far from, like if the benchmark is always infinity, so doing nothing is the best you can do compared to it. So this is less meaningful than comparing to something that is closer to what you can achieve. The second thing is that you can use the new benchmark in order as a tool to design new algorithms. So now that we can design new algorithms, and we'll see some examples of new algorithms developed using new benchmarks, then we can compare the two algorithms. So if I tell you that I can get a 2 approximation to the best offline algorithm, or I can get 1.5 approximation to the best online algorithm, which one do you choose? It's not clear, maybe depending on the instance, but it's better to have more options. And another reason is that new benchmark can help us distinguish between different classes of algorithms. So for example, comparing to profit, we saw that single threshold can achieve the best competitive ratio. This is not longer the case with respect to different benchmark, and you can see the benefit that you can gain by using adaptivity. And lastly, this is a way to measure the importance of knowing the arrival order. So, for example, if you don't know the arrival order, and you can now do like market research and understand the arrival order better, should you exert this effort in order to do so? This might depend on the question of whether this is very close to 1, then maybe it's not worth it. Or if it's far from 1, it might be much like worth to do this research. So, okay. So indeed, many works lately consider the optimum online benchmark. These are all works that in profit settings that in the last few years that compared to the best online optimum instead to offline optimum. And there are still many open problems in this field, like under various feasibility constraints, under you can basically do any work that you do for profit inequality, like doing for samples, doing it for different arrival orders, and consider what you can do in the case that you compete against the online instead of the offline benchmark. And in particular, I want to mention one work from a paper of Soda last year that studied the case of a single choice profit inequality. So what they showed is that indeed, when you compare to the best online algorithm, you can improve from the 2 competitive ratio to phi, which is the golden ratio. So, and phi is tight with respect to deterministic algorithms. And beyond the objective of maximizing the expected value, they also consider the case of maximizing the probability of selecting the maximum value. And there the improvement is more drastic. It's from E to 1.24. In terms of structural observation, they show that while for the profit benchmark, both in the expected value objective and the probability of selecting the maximum objective, that we know that the best algorithm is a single threshold. So when you compete against the best online algorithm, you must use adaptivity. So these 2 algorithms are adaptive, and the adaptive algorithms are necessary for getting this improved results. Adaptive algorithms are the optimal ones with respect to this benchmark. However, in this Soda paper, they assume the following assumption, that whenever you see a reward, you know from which distribution it arrives. So you know that the order up to now, you know which are the observations that you saw. You don't know the order of the future rewards, and you gain more information as you play the game. And in this paper that I'm going to present now, we remove this assumption, and we consider identity blind algorithms that only observe the values. You know the set of distribution in advance, and each time a reward arrives, you only see its value, you don't know its identity and from which distribution it was drawn. So one more thing before I delve into the results. So one difficulty when comparing to the best online is that we don't know what is the benchmark in advance. As we gain more information throughout the game, we learn better what is the best online algorithm, and we know what we are comparing to. So this is one of the main difficulties when you compare against the best online. This is somewhat why you need adaptivity, because the benchmark is adaptive. So it might make sense that also the algorithms will be adaptive. So, okay, so let's see an example. Let's say that we have 3 rewards. One is deterministically square 2. one is deterministically 1, and one is 1 over epsilon with probability epsilon, and 0 otherwise. Okay, so let's say that the square root 2 arrives first, and we need to decide whether to accept it or not. Now we know that the two remaining rewards can arrive in two different orders. So if the deterministic one arrives before the 1 over epsilon, so the smart thing to do is to accept the square root 2. Indeed, the optimum online algorithm would accept the square root 2 and get the value of square root 2. However, in the lower order, when the 1 over epsilon arrives first, it's better to reject the square root 2 because you can get 2 minus epsilon by trying to get the high value, if not settle for the 1. And at the point where the square root 2 arrives, we don't know which of the cases it is. So we can, this is one of the difficulties of compared to the best online. Okay, so this example only consider the case of difficulties of comparing to best online. Now let's see the difficulty in comparing to the best identity blind, like the difficulties of identity blind algorithms. So let's see the following example. We have again 3 boxes. Yes.
Sorry, can I just ask a clarification about the previous example? Is the adversary oblivious, or can they like decide which order after seeing whether you accepted the first square root 2?
So like we assume worst case order after you do this, you set your algorithm. So the result of phi approximation is tight only with respect to deterministic algorithms. And then like you can consider just worst case over orders, but by using randomization, indeed, like you might, it's important to consider which adversary you are competing against. Okay. Okay. So let's move to the example of the identity blind algorithms. So we have again three rewards. One is deterministically half, one is deterministically 0, and one is 1 over epsilon with probability epsilon, and 0 otherwise. Okay, so let's say that we observe 0 at the beginning. So we don't know whether it comes from the green distribution or from the orange distribution. Okay, but it doesn't matter at this point because we'll never accept a value of 0. However, now that we observe the second reward, which is half, we know that it comes from the purple distribution. But now, if we added the information of whether the first one was green or orange, we would have known what to do now. Because we don't know, there are 2 options, and if we select the half, and the first one was the green, we get half instead of 1. And if it was orange and we don't accept it, then we get 1 instead of 1.5. So this is where identity blindness makes things tough. Okay, so let's say our results. So as we said, like when you compete against the best online, you get a better approximation, approximation compared to the benchmark. And we show that like when you observe the identities, you can improve it to phi. However, when we don't see the identities, you lose all this benefit. You cannot get better than the 2 approximation of in the case of the expected value, and for the case of probability of selecting the maximum, you can get something in between. You get 1.779. In terms of structural results, so the best algorithm for the profit we said is a single threshold, and when you compete against the best online, when you observe the identities, like we said that adaptivity is necessary. When we go to the identity blindness gap, to this, when you don't observe the identities, the best thing we can do is again single threshold. Adaptivity doesn't help us anymore. And even in the case of probability of selecting the maximum, where we get something in between, not just like we get the result of, with respect to a profit. Okay, so in the remainder of the talk, I will just mention how we devise the simpler result among the two, how we show that we cannot get better than 2 approximation with respect to the online benchmark. So You might already seen this example. The hard instance of profit inequality when you have two boxes. One is deterministically 1, and one is 1 over epsilon with probability epsilon, and 0 otherwise. So in order to devise a hard instance for the profit with respect to the best online algorithm, it's of course in this example like we can do much better. If you see 1, we know which distribution it comes from, and we always get the optimum. So we need kind of to obscure whether the box, the 1 arrives and whether the 1 over epsilon arrives. So we define a new instance when we replace the deterministic 1 by many boxes. So first we create many boxes that are Bernoulli half. We create also even more boxes that are deterministically 0, and we keep one box that is deterministically 1. Okay, so this is the new instance. So and we keep the box of the 1 over epsilon probability epsilon. And now we need, besides describing the distributions, we need to describe what is the arrival order that of the instance to show the gap between any algorithm that doesn't know the identity to algorithms that know the order of arrival. So if we just design one order, like of course there is an algorithm that can achieve it. So we need to describe either a family of orders or a distribution of over orders by Yao principle. If we want our lower bound to hold with respect to randomized algorithms, it's sufficient to design a distribution over arrival order and show that the best deterministic algorithm cannot achieve more than the two approximation. So now that we have this instance, so what is the distribution over orders? So we take the zeros and we split them randomly into 2. So it doesn't matter like which boxes are where, it's only important how many in each side. Okay, so this is the first thing we do. We basically can split it like each one is independently drawn to each side with probability half. And we take all the purple boxes and put on the left side. And then we put the two special boxes, like the orange box first, and then the deterministic one after between. And the last thing we do is that we shuffle the boxes of the left. So this is the way that we basically design the random order. And if you consider now an algorithm that knows the order, you can always wait until the orange box arrive, select it, and if not, if it's 0, select the blue one. And for an algorithm that doesn't know the order, like it observes like a stream of zeros and 1, and its goal is basically to find the last one among them. And it is impossible to do it with there is enough uncertainty, so it cannot decides to select the 1, and if it misses it, like it gets a 0, one of the zeros in the green ones on the right. Okay, so to summarize, we introduced a new performance measure of the identity blindness gap. We showed the tight guarantees with respect to this new realistic benchmark. In the maximizing expectation, it's the same as in the profit. In the maximizing probability, it's somewhere in between to the best online to the profit. Like in contrast to the order competitive ratio, the measure that when you see the identities, static strategies are sufficient to get the optimal guarantees, at least with respect to the deterministic algorithms. Like for max computation works for both of them, but for max probability it's only with respect to deterministic algorithms. And it measures also the importance of knowing the identities and the arrival order. This type of works like suggests many open questions. For instance, like what can you do when how much can you do better when you have randomization, especially for the case of the max probability, maximum probability of selecting the maximum. Study it in combinatorial settings and other like profit set scenarios. That's it. Thanks. Question?